All right. So for solutions, things that we're looking for is we want to make sure that you can know your intermolecular forces and how that forms with your solutions. We should get this idea about solubility and how that's tied in to our intermolecular forces. We have our concentration units, solubility of solids and gases, and then colligative properties. So a lot of this is kind of review from Chem 120, and it's not a big part of what we cover in Chem 121, but it is part of what they expect you to know for this second semester. And so it kind of bleeds over from Chem 120. So you just want to make sure that you understand these a little bit. So let's start this first one here. If you get stuck and you don't know what to do, then go ahead and put where you're stuck at inside the chat box, and then we can talk about that. Right now, I'm going to give you guys kind of like that 90 seconds to begin. So we're about a minute in right now.
I don't know where the poll is.
It's okay. If you don't have it, hopefully it'll pop up on the next one. All right, so that's 90 seconds right there, right? So most of you guys have put in B, which is what we're looking for. Whenever you see this U-shaped thing and you guys have solutions in it, what property are you guys kind of looking at here? What do we call that change in height between these two volumes of solutions?
Osmosis, or not osmosis, whatever it's called.
So it's osmotic pressure. Very
osmotic pressure.
Right? And so this is an example of a colligative property, right? So osmotic pressure, what happens is we kind of start off looking like this solution here. We start off with them at equal volumes. But when we look at what's dissolved inside, because we have glucose and we have sodium chloride, then we need to think about what's going to happen to that water, right? So water always flows from high concentration to low concentration, or it goes from low concentration to high concentration. It's basically trying to dilute everything. And so when we look at this, what's the difference between glucose and sodium chloride? We have one molality of each, but there's a difference in their colligative properties. Does anyone know why?
The sodium chloride is going to dissociate into ions, and the glucose isn't soluble in water.
So glucose, it's not that it's not soluble. It still dissolves in water. It doesn't dissociate in water, right?
Yeah.
So each glucose stays as one, but each sodium chloride turns into two. So while it's the same amount of solute per mole, it's really twice as many ions. And so that's why we're looking for B here as our answer, because we're going to get twice as many ions in that sodium chloride, so the water is going to flow towards our sodium chloride. And so we're going to get that to be tall. It's going to increase its volume. And here's our next one. So you have about 10 seconds left. And so that's our 90-second mark. All right. And so when we're looking at this one should be pretty straightforward. What type of acid are both of these? We have HCl and we have nitric acid.
Strong.
Strong. So if they're strong, then we know that they can completely disassociate. So if we want to find our H+, then we just need to take their volumes times their molarities. We add them together, and then we divide it by their new volume of the solution. So that's going to be 70. And so if you use them in milliliters, that's fine, as long as you just always stay in milliliters, right? Because their ratios and our concentrations will stay the same. And so we are looking for 4.1 molarity. I feel like that one's a pretty straightforward one. Does anyone have any questions on that before we move on? Okay, here's our next one. So we have a solution of 3 grams of which substance dissolved in 100 grams of water has the highest boiling point. All right, we're coming right up on our 90 seconds. What I would say is think about not only our molality, right, Fry's concentration, but you also want to think about your Van Hoff factor, your I factor as well, right? Remember that boiling point is still a colligative property. So it's about the number of solute particles, not just their concentration. So this one was a tricky one. Okay? So what a lot of you found was that if all of these have an I factor of 1, then this one would be our highest boiling point. It would have our highest concentration. But when we look at them, right, this one is an organic compound. That's why it's a non-electrolyte, stays together as 1. But what do these 3 look like? Are they also organic compounds, or are they going to be electrolytes?
They're going to be electrolytes.
Electrolytes. So B turns into 2 ions, C turns into 4, D turns into 2. And then between B and D, we know that B is going to be better. But between C and B, we know that C is going to be better. So when we look at it, even though its molality or its molar mass is smaller, because it only makes 1, it's not 4 times smaller for its molar mass. So the highest boiling point is actually going to be C.
But don't forces affect boiling point? Like that has 2 hydrogen bonds, and it's a huge molecule, and it's long. Like
forces affect boiling point for the solvent, right? So water, intermolecular forces, that changes things. But we're already saying that they dissolved. And so now what we're looking at isn't about their forces. And the second part about that is that while this one has hydrogen bonds, this one has ion dipole, right? Which is going to be even stronger than hydrogen bonds. And so that's the part to think about with those. But in reality, your intermolecular forces, you don't have to concern as much about that part when you talk about solutions, because this is all driven by the small amount dissolved in the bigger one. So where water's boiling point is, that has to deal with the intermolecular forces. The change from there, that just has to deal with how many particles we dissolve. Let's do another one. All right, and we have 5 seconds left. All right, 90 seconds is up. And so you guys are right that it should be A for our answer. When we think about it, our solubility of our oxygen is kind of like this equilibrium between it being a gas up above, right? The O2 molecule is up above, and being pushed into that water. And so if we want to shift towards more of it being dissolved, then we want to encourage that process. And so if we increase the pressure or the partial pressure of that O2, then that's one way for us to do that. Now, when we do that, when we increase the partial pressure of the O2, we just want to make sure that we keep the external pressure constant. So that way it's kind of like we're getting a greater fraction of that air or that pressure as being oxygen. So in this way, we're kind of increasing our concentration of O2 as a gas, which will allow more of it to go into solution. If we keep O2 constant, right, like for these, it's not really going to change how much or our concentrations of the material, because we're not going to have as much air overall. Okay? And so that's why A is going to be our best bet for increasing that solubility. So a lot of the solution parts are a little bit of a review, right? From Chem 120, you want to be thinking about things like colligative properties, practicing a little bit about identifying intermolecular forces, moving through some of those concentration conversions. Our next section is going to get into our kinetics, right? And so kinetics, there's a couple different things that you have for that. You want to understand the conceptual side, because mathematically there's not a lot of time to solve some of those really more complex kinetic questions that we kind of covered for our exams, right? That's more what you'll see for your final. For the ACS, it's a little bit more straightforward. They will provide you with the integrated rate laws, right? So you will have that part for the questions. You might need to use like Arrhenius's equation to find activation energies. You might need to use plots to identify orders, or you might look at data to identify orders. And so these are kind of like the expectations for your kinetics part. And so we're going to start off with kind of a warm-up one. All right, we have about 5 seconds left. All right. So they're giving us our reaction rate here, right? And they're saying that it is decreasing by 0.20 mole or 20 atmospheres per second. Or not, yeah. So we want to know the rate of change of the partial pressure of N2 for that. So if we're looking at the total pressure, right? Total pressure is another way of talking about moles. So if this is decreasing at a rate of 0.2 ATMs per second, why is it going down? Why do we see a decrease in pressure as this reaction continues?
Is it because the N2 is being used up?
So it's not just the N2 is being used up, right? But if we look at the equation, do we have more moles of gas on the left or on the right?
Left.
Right? We have more on the left. So as we go through our reaction, right, as we move to our right-hand side, we're going to consume our reactants, and we should be going down from 4 moles of gas to just 2. And so we know that we're kind of decreasing, right? And so we can get an idea about how far we're decreasing. So there's kind of like a 4-to-2 ratio there. So if we wanted to think about this, if this is going down at 0.2 atmospheres, that means that we're making this one at a rate of 0.4. If that's being made at 0.4, then our H2 is at 0.3 because of its stoichiometry ratio between there, and our N2 is 0.1 to get that difference. And so I came up with this part here of it being 0.4 because I know that there's going to be that change, that difference. And so we should be going down by half. So if our pressure change is 0.2, then we really should have made twice as much of that product because the ratio is from our forward to our reverse is 2 times. Right?
Wait,
So we have twice as many of these as we have of those.
If our pressure is changing at 2 ATMs, then how is H2 changing at 0.3 ATMs? If
So
the total pressure of gas decrease.
So if H2 is going down by 0.3, because this one is going to be going up by 0.2. So if we're going down by 0.2, that means that overall, our left-hand side has to go down by 0.4. Our right-hand side is going to go up by 0.2.
Right.
Does that kind of make sense?
Yeah.
So this is giving us that change.
It's the wording of total pressure of gas decreases because it's saying.
Yeah. And then the
gas
ratio of your moles of your gas gives you kind of that ratio between them, right? So if this is going down by 0.4, this is going up by 0.2, we can see that as a net, we get that 0.2. And we kind of got this because for every one of these NH3s, or for every 2 NH3 we make, we needed 4 of our reactants, right? So there should be that change there. And so this minus 0.4, 0.3 of it comes from our H2, 0.1 of it comes from our N2, and this one goes up by 0.2. And so that's how we get D. So a lot of you guys still ended up at the right answer, so that's good. But that's kind of the thought behind how you can get there. Here's our next one.
I don't get what it's asking us to. Don't you have to compare 2 different ones?
So they give you a given. So think of that
you're
top one as being
comparing
your
that,
initial.
okay.
Oh,
Okay.
sorry. That is going to be 2 minutes on that one. I was trying to do that calculation too. So when we're looking at this one, right? This first one is our given up here. And so we're kind of comparing against all of them, right? Now, because there's only, if we look at our answers, there's only one possible finding. If you're worried about time, one of the things to do is once you find it, then you can just move on, right? If you're confident that you found the right answer, then you can move on from there. And so if you were lucky and you started out with A, you could really like get through it quickly without doing a whole bunch. The other part is all of these are 10 to the minus 4. And since we're just looking at ratios, then we can kind of take all of those out. We're really just looking at these changes here between them, since they're all at the same scale. So this is a change of 2. This is a change of 5, 4, and 4. And so when we go from A, or from the given to A, we see a change of 2 times here. And if we were to plug that into our rate law, then that should expect it to go up by 2. And so we know A works out. When we compare our given to B, then this went up by 2, and we expect that should go up by 4. But that's not the case. It went up by 5, so we know that that one can't be it. So we know it can't be B. When we look at C, this one went up by 2. This one went up by 2. So now it should be 4 times 2. So it should be a total of 8. So we know that can't be it either. And then this one down here, it went up, or this one stayed the same and went up by 2 here. And so we're expecting to see a change of 2. And so we know it can't be that one. And so the answer is just A.
So how would A prove that it was A squared?
It doesn't prove that it's A squared, but it's consistent with this one here,
All right.
right? Because we didn't change it, it doesn't prove that it has to be A squared, but it does not disprove it. Whereas all these other ones, they disprove that rate law.
All right.
So in this way, they're kind of giving you an easier version of your rate type of the ones that we normally see, where you have to find the rate law from the raw data, because this one's a little bit faster to do. So let's look at our next one. This one is going to be about a plot. And so your exam does like to use some of these graphs, right? And so being able to interpret a graph. We have about 20 seconds left. All right, very good. So when you get into your rate laws, right, a lot of it is about trying to predict when you'll get a straight line. And so when you get the straight line, it's because it's allowing us to kind of get some information about it. It's allowing us to find that rate constant and the time attaching them to the different slopes. Okay? Now this plot is the plot of our rate constant versus this 1 over RT. And so this plot by itself is looking at the temperature dependence of K. Now, do we have an equation that helps us tie in our temperature dependence of K?
Arrhenius's equation.
Right? So this is Arrhenius's equation. And then what factor is also related to that? K and our temperature dependence of it.
Negative EA over R.
It's our activation energy, right? So if we have that K is equal to A E to the activation energy of RT, and then this is going to be negative. If we want to get this slope, then that becomes ln of K divided by A, which is a constant, so it doesn't really matter. E becomes negative EA over R. And this T, or 1 over T, sorry, is going to be our X term. So you can kind of see that this is taking Y equals MX plus B. And so our M is our slope, and so it should be negative EA over R. And that's how you guys came up with that part. Right. So just with your rates, you want to make sure that you have them tied together with why a straight line is important for different ones. Now remember that 0 order, first order, and second order rates, they all give you different types of graphs for your concentration versus your K or your changes, right? And so you just want to make sure that you go through and you have an idea about when should it be 1 over K, when should it be the ln, when should it be those different ones about when it will give you a straight line. For your graph. And so they covered this one inside your guys' textbook. It's, oh, I lost my page now. And so I just wanted to make sure that you can visually identify when it's a first order, second order, and third order equation. And so it's in your book. It's going to be on page 575. They go through, from there, they go over your zero order, first order, and your second order ones. So you just want to make sure that you have those plots of the concentrations over time. In that way, you can visually identify those. Here's going to be our next one. All right, we have 5 seconds left. All right, so I'll start working your way through this. Some of you guys are still wrapping up. That's okay. It's a little bit more of a calculation on this one. So we should have our equation ln K2 K1 is equal to negative the activation energy of R 1 over T2 minus 1 over T1. And so for me, I number them as 1 and 2 to help me keep track. So my K2 over K1 is going to be ln of 6.0 times 10 to the minus 2 divided by 3.0 times 10 to the minus 4. So I get something like 6.396 is equal to negative EA. And then for our R, we should be using that 8.314 joules mole Kelvin. And then I need to turn both of these into their Kelvin. So I take that 6.396. I'm now at negative 53.184 is equal to my activation energy times 1 over 500 minus 1 over 400. And I have a math mistake somewhere in there. All right, fine. Let me go back and double check something. The answer that we are supposed to be looking for should be D. That's what it is. This should be 5.2. And then at the end, we want to make sure that we multiply it by 1,000 in order to get it from, or we need to divide it by 1,000 to go from our joules to our kilojoules. Does anyone have any questions on that part? So whenever you guys get a reaction like this, where you guys have the two that you're trying to compare against, just make sure that you plug into that equation. And then the other part is make sure you convert them all into your Kelvin, right? If you just leave them in the degree Celsius, then it's going to throw off your values because these terms won't be to the same scale for our temperatures. So you want to make sure that you turn them into your Kelvin and then just pay attention to these units here that you stick with your kilojoules. And so we're looking for D here. Okay, we'll try our next one. Give me 1 second, I'm going to grab some water. All right, and so that is our 90 seconds. And so this one should be a pretty straightforward connection between our kinetics and our equilibrium. And so like you guys came up with, it should be our KF over our KR for our equilibrium. Remember that we get K to be equal to products over reactants, and products are the result of our rate of our forward, and reactants are the result of our rate of our reverse. And so KF over KR gives us how much products do you make divided by how much reactants you make. We'll do one more rate one, and then we're going to get into our equilibrium. Now remember that if B is to the -1 power, it's not going to be proportional to it in the very beginning. Right? That means that our B, as it got bigger, our rate would get slower. So that would be inversely related, not proportional. So this one is one of those harder conceptual ones. You have about 10 seconds left. And so you can kind of think that it could be A plus B going to AB all happening at once. But it could be something where we have B going to something. We have A plus C then going to our product. Right? We don't know. It could be one step or it could be many steps. And so what we do know is at low concentrations, then B matters. Right? But at high concentration, it seems to die off. Right? So if it was just rate is equal to K of A and B, like it was a one pot reaction, then no matter what concentration B is, no matter how high it is, it should always still impact our rate. Now, if it was a stoichiometry one, 1 to 2, then that means that as B got bigger, then it should get even bigger. So it can't be that. And if it was the other way, we know that you're right. If it's B to the -1, as B gets bigger, then it kind of levels off. The problem, though, is that when B is small, it shouldn't be proportional to it. It would have to be the other way. So the only one that kind of makes sense is for this to be a two-step reaction. That means that in the beginning, the impact of B matters. That's because as we drive up its concentration, then this first step goes faster. The second part, though, is that when it gets to a really high concentration, then this stops being the limiting step. And this one down here becomes the limiting. Now we've made so much of that product that there's just not enough A to transition it over, which is why our rate starts to level off. And so that's how we get that it should be two steps, and that rate step happens before the rate determining step, or B reacts before the rate determining step. Because we can see that adding in B helps us out in the beginning, but when we get a lot of it, it's not the choke point. The choke point is really A plus C. That's preventing us from moving forward. This one, with it being catalyzed by one of its products, that should be the opposite, that as we see more and more of it, then we should end up making more product and catalyzing it even farther. And so that's what we're looking for, is we're looking for A for that one. Equilibrium is like a huge part of our class. And so you just want to make sure that you are familiar with them, whether that shows up as KP or KC, whether that shows up with our Qs. They shot the A's principle. It also ties into our KAs and our KSPs, right? But all of this is that equilibrium stuff. Now for our class, you have to do ice tables. For your ACS, I haven't seen a problem where you guys really do a strong ice table, or you don't have to solve a quadratic, because there's just no way to solve that in something like 2 minutes, right? So you might have to set up an ice table, and you might have to understand how you can come up with what the X value is, but I haven't seen you guys have to set up an ice table and solve a quadratic for it. But that doesn't mean that for your final exam for our class that you won't have to, because I can almost guarantee you that you will have to do an ice table for our class. But for the ACS, their questions look a little bit more like this. Good. Ahead of the game on this one, right? So remember that when we think about equilibrium expressions, do we include things like solids and liquids?
Oh,
No, right? Nothing that doesn't change its concentration. So solids and liquids have a set density, which means they have a set concentration. So we only worry about things that are gases and aqueous. And so that's why we should have our products over our reactants. So our products are just going to end up being 1 because both of these are constant. Then we have to scale the reactants based on their coefficients. And so that's how we can get our K. Brackets stand for concentration. P stands for pressure, depending on what state you're in. Very good. Let's try another one. So sometimes when you guys are trying to figure out the Chatelier's principle, when it's giving you information, go ahead and add it into your equation. I like to do that with my heats, right? So it's telling me it's exothermic, so now I can add in heat as one of my products. Helps it make it a little bit easier for me to visualize what's going to happen. So if the volume of our reaction vessel is tripled, which direction are we going to shift if we tripled it? So if our volume goes up, do we shift towards the side with more gas or less gas?
Less gas.
We need to shift to the side with more gas, right? So volume is going up, so pressure is going down, so we need to recover that pressure. So we will shift towards our reactants when our volume goes up because we're going to try to recover that pressure. When our volume goes down, then our pressure goes up and we'll shift to the side with less gas to decrease that pressure. Right? So remember that those are inverse. So we're always trying to recover back to that situation. Now, if we cool, which direction are we going to shift? Are we going to shift towards our products or towards our reactants?
Reactants.
So if we're cooling, that means we're removing heat. So we should be shifting to the right to make heat.
If you cool the vessel, doesn't it slow down the particles, meaning it's reducing the pressure?
So that's not, it does slow down the particles, but that doesn't necessarily mean that it's reducing the pressure, right? It is going to, well, so it is going to reduce your pressure for that moment, but that doesn't mean that at equilibrium that it's going to have a reduced pressure, right? It's in fact going to try to recover from that. So if we reduce, well, so if we slow down our products, then what we're going to try to do is try to recover that heat, right? And so if as we move forward, we make heat, then we can do that to help balance us out. And this one is going to shift reactants. Now, if we remove reactant, which direction should we shift? So if we remove Cl2, which direction should we go?
Goes left, right?
Goes left, right? So shift towards our reactants to recover them. And then if we add in krypton gas, what happens with that one?
Nothing.
Nothing, no change. So remember that adding in an inert gas doesn't impact our equilibrium. It's only if we change the volume to increase pressure or decrease pressure, right? Adding in inert gas doesn't change any of that because it doesn't impact our concentrations. So what we're looking for, the only one that lets us shift towards our products is going to be this one, cooling the vessel. And we get that because it's an exothermic reaction. So it looks like that one a little bit rusty for some of us. So we probably want to brush up on those. And so just go back and review your Le Chatelier's principle. Let's look at another one here. So if it helps, do an ice table for this. All right. So this is going to be, oh, sorry. We'll let that continue a little bit longer. So our 90 seconds is up. You guys have about 20 seconds left for your 2 minutes, because this one is a little bit more of a calculation. So the first part is when you have something like this, go ahead and write out your equation. So our equation should be H2 plus I2 going to 2HI. And that's all balanced. So we're all set with that. Right? So we know that we have to have 2HI for it to be balanced. And so this is my initial, my change in my equilibrium. So we started off with 2 of both, no HI. And then I know at equilibrium, I have 3.5 for my HI. So this should be minus X plus 2X. Now, because it went from 0 to 3.5, I can use this one here to solve for my X. 2X is equal to 3.50. So X is 1.75. And so now I can find values for my equilibrium. So I get 0.25 for my H2, 0.25 for my I2. And then I can make my Kc expression right up there. My products squared because there's a 2 coefficient. My reactants, 0.25 times 0.25. And so we're looking for D for our answer. And so that's what I mean for your ACS about solving ice tables. It's still a useful thing to do. You still need to be able to set them up, but you're not going to have to plug them into a quadratic to find out what that X value is going to be. You would have that. Did you guys have any questions about that? Do you want me to go through that slower? Okay. All right, then let's look at this next one here. Well, I'm glad that it seems like we all know that number 1 is not true. Now we just need to be focusing on number 2. So with number 2, right, we're saying that we're adding in O2. And so then we use the Chatelier's principle and we're saying that we're shifting to the right to produce more product. Now, while all of that's going on with Le Chatelier's principle, does it actually change our K value?
No, only temperature can.
Only temperature changes our K value. So while it makes more product, we also have more reactants still. And so when it comes back to equilibrium, it's going to come back to the same ratio of our K when we take into account the products and our reactants. So the only thing that changes our K is going to be us changing the temperature that it happens at, or we have to go through a completely different mechanism. Right? But that same chemical reaction is going to stay the same for its K until we change the temperature. So it should be D. Neither 1 nor 2 is correct for this equation. Then we're going to move on into our acid base. So acid base, there is a little bit of stuff about identifying acids. And so all 3 types are available: Bronston-Lowry, Arrhenius, and Lewis. Both of these kind of stay the same. This is about the H+ and the acceptors and donors. The only difference is that Arrhenius is tied to OH- as well, instead of being an H+ acceptor. Right? Bronston-Lowry is better about that. Lewis is now, when we're looking at electron pair, accepting and donation. So instead of being H+, we're looking at electrons. Buffers seem to come up pretty often, as well as titrations. And then, of course, pH. So you want to make sure that you have that. So for all of the ones that I've seen, our KW has been at the 1.0 times 10 to the minus 14. But if they were to give you a different KW value, they would have to provide that, right? But most of what I've seen has all been at room temperature.
If they give you a different KW, then you just do that new KW divided by your KA or KB.
Yep.
Okay.
Right. And so that would give you your that new relationship. So then instead of 14 minus whatever it would be to get to like POH or whatever,
Right.
you have to use that new KW to find that ratio.
I'm saying if you have KA, you would just do, you would just do that new KW over KA to find KB.
Yes.
All right.
All right. So let's look at this one and let's find out which one is the correct statement for it. or sorry, not the correct one, which one's the incorrect statement for it. So this is going to be the titration curve for an acid and NaOH. So we have about 20 seconds left. So looking at this, this is a, understanding your titration plots is a very big thing for ACS, and actually it's a big thing for our class too, because it ties so often into what's going on with the chemistry of things, right? So just to review, this inflection point here, when it's transitioning from going one direction to the other, what do we call that? This really steep section here, what's happening in the middle of that steep section?
Is it the halfway equivalence or the equivalence?
This is the equivalence point.
All right, equivalence.
At this point, our acid is equal to our base for our moles of acid. Now, that doesn't always happen exactly at a pH of 7, but it can, right, depending on it. Our half equivalence point is going to be where the inflection occurs in here. This is going to be when we stop the, kind of like right when we're getting into the middle of the buffer region. So that's our half equivalence point. Now, why is our half equivalence point important?
Because the pH is equal to the pKa.
Very good. So at that one point, our pH is equal to our pKa. And so that gives us information about our Ka value. So if we're looking at this right now, it's saying the pKa of the acid is 4.0. And so that would be wherever this hits the curve. So is that looking like it's happening in the middle of our buffer region?
No.
No.
No. And so it's not. And so that's kind of why we know that this is not going to be correct, is that our pKa is really much lower, somewhere around like in the 3s, maybe even the 2.7, something like along those lines.
So
Now,
I have a question. Why taking the negative log, the 10 to the negative 2 at the starting point, and it doesn't give you 0.10 molarity? It gives you
because we don't know that concentration. So we wouldn't be able to
find that
use
concentration
its,
because it's monoproduct, and you have the volume, and you can find the concentration of H plus, and then you can find moles of H plus, and since you know it's monoproduct.
well, so we would know how many moles of H plus, we wouldn't know how much of the weak acid they have put in there, because we don't know what fraction of it breaks down. So if 50% of it broke down, then we would know the concentration of the H plus, but we wouldn't know the concentration of the acid.
Got it.
So that works if it's a strong acid. It doesn't work for a weak acid because some of it's still together.
Okay.
So when we added in 15 milliliters, are we to the equivalence point yet? when we add in 15 milliliters of our NaOH, are we at the equivalence point or are we before that? So when we add in the volume of that NaOH, then we know that we're in an equivalence of going to be our, sorry. We know that from here, we're going to be in our buffer region because we're before the equivalence point. You can kind of see that our equivalence point is here at the 20 milliliter marking. And so this is how we find the initial concentration of the acid, right? Is that we can take that 20, multiply it by the 0.5, divide it by the 100 milliliters. And so this gives us the 0.1, which is how many moles of our acid that we took. So we're looking for C in that. Does anyone have any questions on that part? So this last one comes from your equivalence point because we know the concentration of our base, the volume of our base, so we can find the concentration of our acid because we also know the volume of the acid and we know its monoproduct. Let's look at this one. All right, so 90 seconds is up, but we're gonna let this run out a little bit longer. Now, right away, just looking at this, we should be able to tell two things. One is that both of these, A and B, can't be our answer. Right? We know this because this is a weak acid and a strong base salt. That means that we're going to be on the basic side of things. So if we didn't know anything, if we didn't know how to get to that next section, we could at least take out half of them. We could 50-50 it because we should be in a base type solution. So our pH should be less than, or should be more than 7. Now, if we're going to be in a basic setting, do we want to be using Ka?
No.
No. So we're going to be looking at Kb. So we're looking at this part of it, C6H5COO minus plus water going to OH minus and our acetic acid, or not our acetic, it's whatever that one is. And so we need to find Kb. So Kb is going to be 1.0 times 10 to the minus 14 divided by 6.4 times 10 to the minus 5. Right? Now, for the Olympiad, they just give you that equation sheet. And so that's where you get all these constants from. ACS, especially the online one, they seem to be better about pulling some of those constants out for you. But I would recommend just printing out their equation sheet. If you want to get their numbers spot on, then you want to use theirs. They kind of do a little bit of rounding to help you guys out. So like things like Faraday's law, they use like 97,000, things along those lines. Same for their molar masses. But because it's multiple choice and their values are separate enough, if you use the numbers that you are more familiar with, you'll probably end up at the same spot. You'll just be off by a little bit. And so you can choose your closest one. So once we find our KB, I know that this was going to be 0.200. And this is going to be relatively zero. So minus x, x, and x. And so we can have this as being x squared over 0.200 minus x. Now, can we ignore the impact that that x is going to have on point 2? What do you guys think? We can. And the reason why we can ignore it is going to be because that this value is so small in comparison, right? We have a pretty big difference there. The other part is for this, there's like, I have not seen one way to make you guys solve a quadratic, so I wouldn't worry about it, right? So we multiply that by 0.2, we solve for x, and so our x becomes 5.25, or 5.59 times 10 to the minus 6, which is equal to our OH concentration. When we take the negative log of that, that becomes 5.25. But is that our pH or is that our POH? Is this 5.25 our pH? So we should be answering A, or is it going to be our POH?
You have to minus it by 14 minus that number.
Right, so this is our POH, so we need 14 minus 5.25, and that's how we get the 8.75. So for D. No, this one's a little bit different. We haven't seen this type of question before, but we will be able to figure it out. You just have to think about your absorptions here. So right now we start off with a colorless weak acid, but its base is a bright yellow. And so yellow kind of absorbs at 485 nanometers. So we're tracking how yellow it is. All right. So when we're looking at this, when we first start off, we're starting off with our colorless solution, right? So when we're thinking about a colorless solution, at the initial point, are we gonna have any absorption in that yellow region?
No.
No, right? So we're looking for something that doesn't have any absorption in that yellow region as we begin with. Because our pKa is so very small, right? We should have a very, very, very tiny amount of the conjugate base. So that's why we're not looking for C or D, because we shouldn't really have much of that base there. We shouldn't be seeing much of that color. As we start to titrate that, the amount of our conjugate base increases because we are slowly turning that weak acid into its base. So that should be gradually going up until all of it transitions over, and then it will stay constant. So if you kind of think of this concentration as being our OH minus, or not our OH minus, sorry, our A minus, we're going to start off extremely small, and then we're going to build up, and then it's going to kind of plateau out. And then over time, our absorption actually will start to come down a little bit as we dilute it with more and more of that sodium hydroxide. Right? So we're really looking for B here, because in general, it's going to go up until we get to our equivalence point, and then it's basically going to stay the same as we've now turned all of that HA to A minus. The problem with C here is that you're starting off with a lot of A minus, which isn't the case for our pKa. And so that's the thing to consider with that part. Does anyone have any questions on that part? These next two ones should be pretty quick, right? So we're just gonna, this is one of those ones where you can use it to kind of regain some time. So which of these salts is gonna form a basic aqueous solution? All right, very good. It should be A. And so we're just looking for our strong base, weak acid. And so out of HF, HBr, HCl, and HNO3, we know that HF is our only weak acid. On the other side, we knew all of these should be strong bases because they're all metals and then ammonium. Okay, very good. Let's go on to this one. And for timing wise, that was about 45 seconds. And so that's a way to kind of recover some of that time if you feel like you've been falling a little behind on them. Now, anytime it's talking about buffers, you should be thinking of our Henderson's equation, the Henderson-Hasselbalch equation. All right, 90 seconds is up. So when you guys are looking at this one, right away, which two answers can we throw out? If we think about our buffer solution, right, we have a weak acid and its conjugate base. And so are we always going to be on the acidic side, or are we going to be on the basic side? If we have a weak acid and its conjugate base, are we going to be on the acidic side, or are we going to be on the basic side? It doesn't matter how much of its salt that we add in, we're always going to be on the acidic side, right? So what we're looking at here is we can take out C and D because those are going to be base values. That's going to be once we neutralize the acidic acid and we're adding in that NaOH. So we just need to go ahead and add in this part here, log of A minus over HA. So this one is A minus, this one is our HA. And because we have equal volumes of them, we can just use their values as they are. If they weren't equal volumes, we'd have to adjust them for that new concentration. But because they are equal volumes, then their ratios will stay the same. And then we have negative log of 1.8 times 10 to the minus 5 plus that value there. And so our pH, once we plug that in, is going to end up being this 4.83. And so that's kind of how we get through that. Now, I know that we're running a little bit over, right? If you feel like you need to go, then that's not a problem. We still have a couple of different topics that we'll go through. We'll kind of narrow it down and we'll hit them a little bit faster. And I will record this, so I'll post the rest of it to YouTube later if you're not able to stick around and finish it off. Okay. So the next section is going to be on solubility equilibria. So this is going to be things like our KSPs. This is also going to be things with our common ions. So remember that KSP is not the same as solubility. So let's find which of these is going to have the greatest molar solubility in water. And so they've given us their formulas and they've given us their KSPs. So remember that KSP is about once they dissolve. So you can only use KSP to estimate molar solubilities when they are all the same number of ions. If they're not, then you really have to translate that out. Right? So remember that KSP is kind of our ions of Zn and C2O4. And we would get an equal ratio. So we can find their solubilities by looking for that S squared when it's only 2 ions. When it's 3 ions, then it becomes something a little bit different. That 3.9 times 10 to the minus 11 is equal to our calcium and our fluorine squared. And then this is going to be S, this is going to be 2S squared, which is really 4S to the third. So we end up finding them slightly differently. And when we go through and we do that, the 3.9 times 10 to the minus 11, we divide that by 4, We take 1/3 of it. Oh, sorry, not divided by 1/3. We get times 10 to the minus 4, whereas this one is going to be 2.7 times 10 to the minus 8. Square root of that. We can see that our calcium fluoride is just that little bit higher in its solubility than our zinc. So you have to make sure that you take into account all of the different ions that it can break down into. So don't just look at your KSP, look at your number of ions as well. ACS likes to throw those little curveballs at you.
Wait, you
So
did
make sure that you take into account.
you did 3.9 times 10 to the negative 11 divided by 4, and then did 3 root of that value.
Yes.
I get a bigger number. I get 9.367 times 10 to the negative 6. 3.9 times 10 to the negative 11 divided by 4, and then you
So
take
3.9 times 10 to the minus 11 should give us 9.75 times 10 to the minus 12.
right, and then take 3 root that number
Yeah, so I do that to the 1/3.
to the 1/3.
That's the same as
Oh,
taking
yeah,
a
yeah.
cubic root. And
And
so,
and I get 0.00009367.
so take that number that you have and cube it.
Cube that last one.
So double check, because if I take 2.136 times 10 to the minus 4, and I take that to the third power, I get 9.75 times 10 to the minus 12. If yours is to 10 to the minus
You said
6,
you get, if you take what it was, to say that again.
so take your answer
Okay.
and put it up to the third power, because you should be, if it's 10 to the minus 6, you should be up in like 10 to the minus 18.
Yep. So why am I, but I'm doing exactly the math.
So look at your calculator. If you're doing 3 cubed like
Right.
that, you might just be doing your calculator 3 times the square root of 9.75 times 10 to the minus 12.
But
You would
isn't that
need
how you cancel a 3 root?
no. So to do a cubic root on the calculator, you would need a little 3 that sits on top in that range there. If you just do 3 and then the square root, one for your, then you're doing 3 times that. So that's why I do to the 1/3 power, because then you're going to get the cubic root.
Yeah, okay. That's probably what I was doing.
Okay. We're going to look at a KF equation here. Now, this one I think is one of those more complicated ones. I think it's a very interesting one, but it's a little bit of a challenge for sure. So we're at 2 minutes for this one. Okay. This would definitely be a question that I would recommend flagging and then coming back at the end if you have enough time to do it. So I'm going to do this on the whiteboard so we can kind of see a little bit more space of what's going on. So we kind of have two processes. We have the dissolution of our silver, and we have the formation of our metal ion. Now this one has a K value of 1.8 times 10 to the minus 10. This one has a K value of 1.0 times 10 to the 8. And so if we look at that entire process, that means that the dissolution of that silver plus the ammonia to make the silver containing metal complex and the chlorine minus should have a K value of our KSP times our KF, right? So if we add the equations, then we need to multiply their Ks. So 1.8 times 10 to the minus 10 times 1.0 times 10 to the 8, and we get 1.8 times 10 to the minus 2. So our K expression looks like 1.8 times 10 to the minus 2 is equal to our chlorine, our silver NH3, all divided by 2, or sorry. There we go. Our NH3 squared. Do you guys have any questions on that part being set up so far? Okay. So I'm going to go ahead and build out my ice table a little bit. I don't need to worry about this one because it's a solid. My NH3, I don't know what we need here. That's what we're looking for. I know that this one is going to be 0, and this is going to be 0 as well. I know that when we go through that change, this is going to be our X value. This is going to be minus 2X, and this is going to be our X value. And we get that Cl is going to be X because for every 1 silver that we need, then 1 Cl needs to get produced. And then the interesting part is that we do know how much of that AgCl we need to have dissolved at the very end. We need to dissolve 0.01 moles of it at 1 liter, and so that gives us a concentration of 0.01. That means that this is going to have a concentration of 0.01. And then this one is going to be NH3 of its initial minus 2X. So we get 1.8 times 10 to the minus 2 is equal to 0.01, 0.01. And then this is NH3, our initial minus 0.02. And we can find our NH3 now. So 1.8. So 0.01 squared becomes 0.1234 divided by
Wait, sorry, I can't see the question anymore. Where'd you get the 0.01s from?
Yep. So if we go
And
back to our
0.02.
question, right? I took the amount of our AgCl that we need to dissolve, and then I divided it by the 1 liter. So I took the 0.01 and I divided by the 1 liter, and that's giving me the concentration of that Cl minus that would have to be there when finally we've dissolved all of that. Hmm?
But isn't AgCl a solid?
So AgCl is a solid, so that's why we're not including it in our ice table. What we're saying is that when all of that AgCl dissolved, then it would make so much Cl ion,
Okay.
right? And because of 1-to-1, then if we know how much AgCl dissolved, then we know how much Cl minus we should have. And so once we have those together, sorry, trying to get this cup back up here. We should be able to find that our concentration of our NH3 plus, when we flip it, we get something that looks like, sorry, I lost my whiteboard. Can you guys see the whiteboard again?
Yeah.
Okay. So I'm going to bring up this NH3 over here. So this is squared, right? Because we have to square that whole value. And so this becomes something that looks like 1.8 times 10 to the minus 2. 0.01 NH3 minus 0.02. And then I'm taking the 1.8 times 10 to the minus 2 and I'm square rooting that. Right? Because basically I could take out all of a square from each side. And that becomes NH3, our initial concentration, minus 0.02 is equal to 0.01 divided by 0.1342. And so this is our concentration for our initial NH3. And since there's 1 liter of it, then we get 0.095 moles. So if we go back to our question, you can see that it should be C. Now this is like a very complicated problem. And with your 2 minutes, it becomes quite a challenge to do. So I wouldn't worry about some of these. These are more like the cherry on top. So this is what happens when you kind of work your way through. And if you have time at the end, then I would tackle a problem that looks like this. Because it is involved. And to get all the way through, will take probably more than your 2 minutes, right? And so you just want to keep that in mind as you're solving some of these. The entire exam is curved. So for some of these questions, if you don't get enough time to solve them, that's okay. Focus on the ones that you do know, focus on the ones you can solve. What you don't want to have happen is that you see this problem, you spend 15 minutes doing it, and in that time, you don't get to finish the last 7 problems of the exam, right? So when you see some of these ones, you want to flag it and come back to it, because time is a little bit of an issue here, right? And so you want to make sure that you take care of the ones that you really know how to do, and then come back to tackle these a little bit later.
Sorry, quick question. Two quick
Mhm.
questions. So I know that you got your 0.01 concentrated molarity for Cl. That's by doing that. But did you also come up with the fact that you have 0.01 of the complex ion there would only be 0.01 molarity available of silver?
So if we want to use up, if we want to dissolve all of this compound, right, the AgCl,
Right.
then we do know that 0.01 has to go towards the Cl minus. And then we know that this complex, because it lies so heavy to the product side, then it should be the same, right? That we're going to make as much of that Ag or the silver complex as we have the silver available.
And then that -2 that came from that minus 0.02.
That's because we had the concentration of our NH3 from the beginning, and we had to subtract 2 times the concentration of the silver complex from the end. So when we're doing that ice table, we're starting off with the 0.02 is coming from the like the mole ratio, which we can convert into the molarity because it's 1 liter.
So you're just doing 2 of, it's just the ratio between AgCl and NH3.
Right, so when I'm looking at this one had to go down by -2x.
Right.
In order for these to be made because of our equation.
Right.
Yeah.
So it's just always going to be double what the concentration of.
So you're looking from your combined equation, we're looking at the coefficients, right? So this one is a 2. So if this one up by x, then this one has to go down by 2x.
Got it.
Yeah. So you just have to combine the equations and then balance them. This is a little bit more reasonable for what they will be looking at for your solubilities, right? And so they're having you guys compare between these two, or these 3 solutions. And this should be a capital O here. And then this should be a lowercase 2. So it should be Ag2CrO4. All right, so that's going to be our 90 seconds right there. And so when we're looking at this, when we think about solubilities, what condition should we be kind of thinking of when we're looking at whether it should dissolve more in pure water or these other two solutions?
It would be like Le Chatelier's principle.
So a little bit about the Chatelier's principle. And why these other things are going to matter is only if there's a common ion. Right? Because if there's a common ion, then it's going to change our principle because we would have more products already there than if it wasn't. So in pure water, there's no common ion. So as much of it can dissolve as it can dissolve. When we look at these other solutions, they both share an ion with our AgCrO4. So on number 2, it shares Ag+. On number 3, it shares CrO4. Now, if they were both 1-to-1s, right, then they would impact them the same way. But because one of them is, so our KSP equation is kind of like Ag plus squared in CrO4, 2 minus. The silver ion, is that going to have a bigger impact or a smaller impact compared to the chromate ion being present? Is that going to prevent, so us having the same amount of Ag plus compared to the chromate, is that going to prevent less material from dissolving, or is it going to allow more material to dissolve? If we think about it, the fact that it's being squared means that not as much material is going to be able to dissolve of this CrO4. In order to make that true, compared to our CrO4, because we're taking the concentration of it, we're squaring it. So 0.1 squared gives us a different value than if it was just 0.1. Right? So we should be looking for D here, because this is going to suppress that dissolution at a much higher rate than our chromate ion because of that squared impact. And so that's what we're looking for, is we're looking for D. Thermodynamics is a combination of spontaneity, entropy, and our equilibrium can get tied in there. So make sure that for equilibriums, we know the difference between Q versus K. You do want to have an idea about being able to predict your entropies, right? So if things are going from a solid to a liquid, did they increase in entropy or decrease in entropy? And so we're going to look at this one as our example for our thermodynamics. So we can run these both together. And so when we look at 23, which of them is going to have our greatest change in entropy? What do you think? Like if we look at A here, is that even going to be a positive change in entropy? So it's not going to be a positive change because we're taking our moles of gas and we're going down in them. We'll also be becoming more connected, right? So it's not going to be A because that's not positive. D, we're going from 3 moles to only 2 moles. So that's also not going to be there. Now for B, we go from 7 to 4. which is also bad, but we also make a liquid out of that, which is also working against us. But if we look at C, we're increasing our moles of our gas, plus we're going from a solid to a gas. And so that's going to give us our best positive change. Right? So you really want to be comparing moles of gas as well as your state changes when we're looking for entropy change. So positive means we're moving towards disorder. So we need more gas. If there's no gas, then you're looking from going from solids to liquids or from solids to being dissolved, aqueous, the ions. And so let's look at this one. So we know our delta H is positive. How is our delta S for this reaction down below? What do you guys think? What should our entropy change look like for question 24? All right. So we have 2 moles of gas and we're going to 3 moles of gas. So it should be a positive change there. And so if we're talking about spontaneity, spontaneity should always bring up delta G in your mind. And so delta G is delta H minus T delta S. And so if this is positive and this is positive, we're going to be spontaneous when delta G is negative.
So it has to be low temperatures.
Right? So if we're minusing T times a positive number, if we go to low temperatures, this term over here is going to be getting smaller, right? As that T shrinks, then our negative value is going to shrink. So low temperatures isn't going to help us. Right? As this goes up, right? As our temperature increases, this term will become bigger and then we'll get to that negative side. So you can kind of imagine that if you put in 0 here for our temperature, our delta G is going to be positive, and so it's going to be non-spontaneous. So we know that it can't be spontaneous at all temperatures, because if we put a 0 there, then it's going to be positive. If we make that a -1, which doesn't really make sense because it's going to be in Kelvin, but if we kind of make that a smaller value, then our negative T might not have enough to overcome that positive of that delta H. But if we go high enough, we can eventually make this term big enough to overcome that delta H. And so this is going to be when it finally becomes spontaneous, which is at high temperatures. Spontaneity at low temperatures is the opposite situation. This is when delta H is negative and our delta S is negative. That means as our temperatures get lower and lower, then our delta S becomes bigger and bigger, basically. And then if this is a positive and this one is a negative, then it's never spontaneous. And so that's our thermodynamics. There's some more practice problems in there as well, and you can work your way through that. We only have 2 other topics I want to touch on. One's electrochemistry, and then the other one is nuclear. Electrochemistry, a lot of it focuses on galvanic cells, and so finding your delta E's. There's some that does your electrolytic ones, so making sure that you can take your currents and turn them into the amount of material. And then you have some that uses your Nernst equation, so it ties in your concentration impacts. So let's try this one here. Now remember, current is your is per second. So an amp is a coulomb per second.
So on this one, the moles of electrons is equal to the moles.
Is it? If we're trying to take our nickel 2+ out
And to turn it into nickel.
and to turn it into nickel,
So it's ×2 and then divided by the volume.
right? Do you want to times it by 2 or do you want to divide it by 2?
If you're trying to cancel mole electrons. Oh shit. Yeah. You want to divide it by 2. And then divide it by 2. What? One mole electron. Right. If you divide that by 2. Oh. Yeah. Okay. I changed my answer. So what is that? Is the wording deposit? Is that how you know?
So we know because it's saying that it's nickel, right? Deposit just means that it's going to be a solid, so solid nickel, and then that can give us an idea. But if they just said that using a current to convert all of the nickel 2+ to nickel, we should also know that it's going to be Ni with 0 oxidation, right? Because we're making this solid. And so once you go ahead and you go through this one, then the answer that we are looking for is going to be C. Right? So 126.5 times 60 to get us in seconds times 5.15 divided by our Coulomb's law divided by 2 divided by 0.225. And so we should be looking for C for that. Right? And so this is kind of the setup there. So there are some electrolysis problems that do show up. So you do want to practice that. This could be the other part, right? So they could give you your redox, your standard reduction potentials, and then try to have you put together a cell, right? So in this case, we're trying to go from chromium 2+ to CRS. And so we have to figure out that overall reaction, right? So that's CR3+ going to CR solid. And then we should have this one, CR2+ going to CR3+. And so now we know which direction we should have our equations. So this could be negative 0.73. This should be a positive 0.50. And then I just go ahead and add those together. And so I should get a minus 0.23 volts. And then on the other side, for this second one here, what is observed is if a piece of lead is placed in an aqueous solution, is we want to be thinking about what's going to happen. So if we are in an aqueous solution, we're going to be this copper 2+. And so as this goes through that process, we're putting in lead solid and we have copper 2+. Now, are they in the correct relationship here about who wants to be an ion versus who wants to be a solid?
No, you have to switch the PB reaction.
Right? So normally, because this one is negative, that's harder for us to, or it is less likely that it's going to be in the solid state compared to the positive reduction of the copper, right? So the more positive you are, the easier it is for us to reduce you. The more negative you are, the harder it is for us to reduce you. So this lead should be becoming more lead 2+, and this copper should be moving towards being more copper solid because the copper is the more positive value. So it's going to be the one that reduces. And so for these statements, which one would be true? Does the mass of the metal increase?
Well, copper is increasing.
So the copper is increasing, but it might not be the lead, right?
That's what I was asking. That's what I was going to ask. Is it the mass of
Yeah.
the lead or the mass of the copper?
So this would be the mass of the lead because they're trying to say it's the mass of the lead piece that you put in.
So then it would only be B.
So it's going to be only B. But I get what you're saying, that if you considered that the copper could be forming on the lead, then it would confuse things. Right?
No, I was saying the copper is forming on the copper anode, is going from copper ions to copper solids. So that's what I was saying. There's no clarification on which metal. I assumed it was lead.
So for this one, there's actually no anode, no cathode.
Oh, but in the question it says piece of lead. Okay.
Yeah. So that's all, right? And so there's some more electrochemistry problems. You can do that. They have you guys like balance coefficients. Just the thing to remember is that if you are gonna balance an oxidation reduction reaction, is make sure to balance the number of electrons as well. So not just the species, but also your number of electrons. Nuclear chemistry is pretty straightforward. It's staying with your radioactive decays. There's the chance that half-life could be on there as well. But most of the ones that I found with something like this, which is what's the missing particle, right? Or they tell you if it goes through alpha decay, what is the daughter nucleus? So like that type of problem, right? So what you want to do is just make sure that you keep your mass numbers consistent. So this would have to be a 4 in order to balance our mass numbers. This would have to be a 2. And so from there, I know that that one has to be helium in order to keep that true. They could also phrase that same question, positron emission, right? So positrons, do they have any mass?
Positron emission that's when an electron is shot out of the proton, right?
So that would be an electron decay, right? It doesn't mean that we're emitting something. So we are going to lose this particle. But a positron, is that a proton, neutron, or electron, or is that a new particle?
It's a proton.
So a positron is a
no. It's a positive particle from the neutron, right?
So it's like an electron, except it's the positive one.
Right.
So it's like the opposite of an electron. So that's why they call it a positron.
It comes from the neutron, right?
So it comes from the neutron when it decays into, it comes from the proton when it decays into a neutron. Right? So it gives away something with no mass, but it's got a positive charge. Right? So if we go through that positron decay, so then we're taking with 218, 84 PO, and we're releasing one of those. I guess it's really a B.
So it'd be bismuth.
So it should be 218, 83, and that's going to be bismuth. Right? Now, for you guys' exam, they include a lot of images of them, but some of the images were not as clear. So I've gone ahead and I've clarified them down below. Canvas doesn't let me stack numbers like this. So I just call this one polonium 218 because we should know how that relates to those, right? And you guys have a periodic table, so you can figure that part out as well. But I've also included the images above. So they do okay. You should be able to see them. But if not, I also have the names down below for them. And so you might do whole reactions for them, or it could just be these different sections. And that's basically all of the ACS review for it. What I would say is the timing seems to be where people struggle the most because it feels a lot more like a standardized testing strategy. So you just want to make sure that you practice with time a little bit, and also that you don't let yourself get stuck on one problem. Start and come back to it, right? So this is where it's really nice to have scratch paper, so you can just write down the numbers of things, like write down the numbers of questions that you don't know that you want to guess on, and then write down ones of things that you do know but you need more time, and then just nail out the ones that you kind of feel really confident of that you can solve quickly. And then so normally for an exam like this, I do 3 passes, right? I do 1 pass where I just take out all the easy ones. Then I do a second pass where I do the ones that I know how to do, but take a little bit more time to do those calculations. And then I come back the 3rd time and I kind of wrestle with those hard ones where I might have been stumped on, or where I'm just going to go ahead and guess. There's no penalty for guessing. So at the very end, you should just go through and click a whole bunch of them for that. That is the thing about multiple choice. Even if you know nothing, you could still get 25% just by randomly choosing. So just keep that in mind as you work your way through. A lot of times, you should at least be able to narrow out some of those choices, even if you don't have time to do all of the math. Kind of like what we're doing with the buffer solution.
So so a positron emission is a plus electron, a beta decay is a minus electron, alpha decay is -4 neutron mass, and then minus 2 protons or electrons, whatever you want to remember. And then what's the other one where
it is
nucleus?
Electron capture. And so that is when an electron comes into the nucleus. And so you just take the electron, but you put it on your reactant side.
And that's the proton, one proton?
So that's when so it's just like, it's literally like you're adding an electron in. So if we wrote that out, it would be 230. Right? So it would look like that.
That's electron capture?
That's electron capture, because you capture
and then what's beta decay? Beta decay is the same thing.
Beta decay is 230, 90, but you release an electron.
On the other side, right. Okay.
On the other side. So it's all about where they are.
What's the
so
one
those are the big
1 over 1p?
1 over 1p is if you were to release a proton, right? There's not a shorthand name for that one. Okay. But that would be if it went through proton decay or released a proton, right? In the same way that you could have neutron capture, or you could release a neutron as well when you like go through fission, but it's not one of the 4 shorthand.
Yeah, like this one right here, D, like D. What would that be called? That's the one you're talking about? No, go back. Yeah, D.
So this would be a neutron. So this is just a neutron. So this is if you gain a neutron or lose a neutron.
So that's just like if you were balancing an equation.
Exactly.
Okay.
Right. So if it's 1 over 0, then it has to be a neutron. If it's 1 over 1, that has to be a proton. If it's 0 over -1, that's an electron.
But like the only time you would use those is if you were just balancing an equation.
Yeah, or if they explained in words that like this one fissions, you produce a daughter isotope and 3 neutrons, then you would say, okay, this one fission, we have 3 neutrons, and then we have the unknown. And so then we would have to figure that out, and that would be 227. This would be 90. Oh, sorry, I don't need it. And then we would figure out that part.
Okay.
All right. Perfect.